All right, so if there are no further questions, let's get into lecture 1. It's a quick lecture. We're going to look at some properties of signals and systems that we need to define before we start modeling systems. All right, so before we even do that, let's talk about some applications of what we're going to cover in this course. So as I said in the beginning, we are interested in systems that can be controlled to perform a given task, to achieve a certain performance. And here I have a few examples. So the first one is a automated insulin dosing system that is there to control the sugar level in the blood automatically. How does this work? What are the main elements involved in such a system that is able to regulate the content of sugar or glucose in the blood? Well, we need certain specific parts. The first one would certainly be a way to measure your current blood glucose level. The other one would be a way to inject insulin in the system, in the body, take that information, see how the body reacts to that, and then adjust how much we are still inserting in the body. So if we were to draw a very rough schematic of all pieces that compose the system, we would need to first have a desired level. This desired level will have to be compared with the current level. And then we create some sort of error. We want the level to be 10% higher, 10% would probably kill, but 1% higher, 1% lower, and so on. Based on this, we can now make a decision on how much insulin we should inject in the system. So here we need some sort of controller that will take this information into account and determine how many milligrams, for example, we should inject in the body. This then goes to what we can call here a delivery system that now applies a certain specific amount of insulin in the body. So here we have the amount that goes in the body. Here we have the body. And the body reacts. So here we have the effect of that injection. And the effect of that injection now needs to be somehow measured so that we can determine the current level. So we can put here a sensor. And this sensor measures the effect of this dose of insulin in the body. And that will now close our loop. So when you close the loop like that, what are we doing? We're actively monitoring the glucose level in the body and make adjustments on how much insulin we are injecting to keep that at a desired level. And this desired level is the reference level that we have right there. Okay. The controller is something that we need to define. What is this logic? If we want to go X% above the current level, how much should we inject? What is that logic there? This is something that we as engineers will have to define. The delivery system is also something we need to take into consideration. What is the action we need to take if we have a small actuator, a syringe or something that is pressing, pushing insulin in the body? How does that work? What is the commanded action? What is the output of that system? Once that is injected into the body, we can't really model the body, but we can have a fairly good idea of the effects of injecting X amount of insulin. We take the effect and you close up the loop. And now this loop is actively monitoring the system. So we see key parts here. We see the controller portion, we see the system we want to control, and we see the sensor that we use to measure that. So we're going to mostly focus on the controller and understanding the system that we want to control, and then creating this closed loop system that will actively monitor what we are trying to control in the system. So this might be a bit fuzzy at this point, but we're going to now work on these specific blocks and then put everything together, and hopefully that will be a bit more clear.
Professor,
Here,
just
yes.
have a quick
Yes.
question. So this monitoring usually based on a time miner or based on the quality or the volume miner?
So based on the quality or
and the quantity or the
quantity?
volume miner?
Yes, based on the quantity of the glucose level in the blood that we need.
Okay, so it will also based on the time miner.
Sorry, I'm not sure if I understand. Based on
the time miner.
The time miner.
Yes, it will like to measure or monitoring based on a certain kind of period.
Right. Correct. So correct. The system takes some time to react, right?
Okay.
And so we need to let the system settle at a given point and then take actions based on that. Let's say we injected X amount and then we raised the level by half of what we wanted. So the system will automatically realize that, okay, now we need to increment that a bit more to get to the level we need, right? So that loop will take care of this, what you can call the response time of the whole system, of the body to, or the reaction of the body to an injection.
Okay, good to know. Thank you.
Here I have another example. So this is a ventricular assisted device in an artificial heart. And the idea here is to compensate for deficiencies in the heart and to regulate blood pressure. How does this thing work? What do we need? What are the elements we would need to regulate the blood pressure in this system? Well, first, we need a target blood pressure, a reference body blood pressure, or a desired body pressure. Then you need to measure the actual body pressure. I keep saying body. Blood pressure. We create a error. And now we need to command this pump that replaces the heart to pump more or less blood such that we reach the desired pressure. So this is another example that can fall exactly in this schematic here, where you have the controller, we have the system you want to control, and we have a sensor, a desired reference, and the system works in a closed loop. And here it is regulating the blood pressure. Here is another application. We have mind-controlled prosthesis. Here's one example. We have a mechanical device that is attached to an arm, and this mechanical device is basically replacing the limb. And how can we control this one? Let's say we want the individual to move the limb from point A to point B. What we could do is to attach something to the arm to measure the muscle activity, take that muscle activity as a desired intention to move the arm from position A to position B, and then control the arm to go from position A to position B. So you have, again, the same structure. We have a desired position that you're now taking from this muscle activation signals. We have the current position of the arm. We know it's a robotic system. We know where it is. We create an error. We create a desired motion. That goes to a controller that will now determine how much we need to actuate a motor, a servo motor, or something inside of that prosthetic arm to move from A to B. And when you get to point B, then the system stops and waits for the next signal and so on. Right? That works in a closed loop. Another one that I'm particularly interested in is robotic surgery. Some of my research, most of my research is on robotic surgery. How can you control robots to do a surgery, let's say in a moving heart? Instead of stopping the heart to do heart surgery, we want to let the heart keep beating, and then we want a robot to go inside the heart and do some operations in the heart. We now need to measure the heart beating and need to control the robot so that it follows the heart, but it also is also able to do some sort of intervention in the beating heart. Or eye surgery, for example, if you want the robot to puncture a small needle through the eye to reduce pressure in the eye, a very common procedure. How can we do that? We need to be very, very precise. We cannot let that puncture be more than a certain amount. Less than a certain amount wouldn't work. The system needs to be stable. How do we develop all that knowing the physiology of the eye? How do we integrate that information in this control system? So these are simple examples. Can you guys think about anything else where such framework would also apply in biomedical systems? Does anybody have?
The infusion pump.
The infusion pump, yeah. It could also be for anesthesia, for example. We could control the level of anesthesia with an infusion pump. Anything else?
What about like MRIs and CAT scan devices, those types of things?
Very good, very good. We could control these devices, for example, to focus their magnetic field specifically at a given point. So we need to time all the coils such that the focus of the magnetic field is very precise, and we can move that. Ultrasound systems controlled by robots, for example, are another example of it, where a robot holds an ultrasound probe and then scans the tissue automatically. Very good. What else?
Ventilators.
Ventilators, excellent, excellent. Ventilators, we can control two things in ventilators. We can control the pressure, or we can control the airflow. We need to measure how the patient responds to that. And then we want the ventilator to always maintain, let's say, a certain pressure or a certain airflow, or even both, as the patient breathes. Anything else?
The IABP is the intra-aortic balloon recharge pump.
Okay. That, I'm not too familiar with that one, but
yes, it's something similar like it's something similar like the heart pump, but it's usually used in the ICU.
Okay, excellent. And these examples go on and on. Here I have a few more: artificial muscles for modeling and control, tissue characterization, micro electromechanical systems, so tiny robots that you can insert in the body to go through a vein and do some sort of operation, artificial eyes for the blind, teleoperated surgery such as the Da Vinci system, rehabilitation devices, health monitoring implants, and the list goes on. Okay, so applications of what we are going to see here are literally everywhere in biomedical systems. Now, we are taking a biomedical system and we are developing another system around it to control it. And this is what we call control engineering. So let's define some key aspects of control engineering first. So the first thing we need to establish here is what we want to control, and we're going to call that the process. The process is a system that reacts to a given input. In the case of the body, we would put in a certain amount of insulin, and the output would be a new level of glucose in the blood. The process, in this course, will be represented by a mathematical model. If we are dealing with a mechanical system, we need to describe all the differential equations that govern that system, and then that will give us this relation between the input and the output of the system. So the first step in control engineering is always to understand what we want to control. Right? And this system is a system that has certain properties that you're going to define later, such as linearity, causality, and other specific properties. And they are assumed here as a simplified version of a real system. Then once we have the process, we need an actuator. An actuator is something that will act on the system to change the behavior of this system. So this actuator could be a pump, could be a servo motor, something like that. And finally, we need a controller. The controller now is the logic of control. We have a desired response. We have knowledge about the process. We know the actuator. So the controller now decides how the actuator operates on this process to bring the output to a desired response. This is what we call in control engineering a open loop strategy, because there is no, you apply something to the system, we let it run, and we don't watch the output. We trust that we know the system well enough so that it will do what we expect it to do. But this is not always the case. It's not always the case because we don't necessarily have a perfect understanding of the process. So instead of using an open loop, we can use a closed loop. And closed loop is the example, first example I gave to you, where we are now monitoring the output using a sensor. And we are creating an error signal here. This error signal is now the difference between the desired output and the current output. If the error is non-zero, that means that we are not where we want, and you need to take actions to bring the system there. And if the error is zero, then the desired response and the actual response are precisely the same. No need to act on the system. So this is called a closed loop system, where now we are taking active actions to monitor the behavior of the system. This is a much better solution because here we can now compensate for external elements acting on the system. That we are going to, which we are going to call a disturbance. Let's, for example, think about a temperature control in a house. If I have a temperature control in my house, I set the desired response to 21 degrees. The system works, the house settles at 21 degrees. And all of a sudden, the external temperature in the house changes by 10 degrees. Of course, my output will adjust because of the external temperature change. And you see this temperature change is external to the system, is not part of the process. It's something acting on the process that it cannot be modeled, and then it is an external source to this process. So by having this closed loop strategy, we are now some sort of immune to these external disturbances that may act on the system. Another advantage is that once we measure anything in instrumentation, we always introduce noise to the system. So this strategy also makes our control problem robust to any noise that may act on the system. So now that we have a system to control, this system needs to be modeled mathematically. And you're going to have to make here some assumptions because systems in reality are quite complicated. We can approximate that system with a mathematical model to the best of our abilities, but there's always going to be certain discrepancies between what we model and how the system operates. This is to say that we need to make some assumptions. The first assumption is that the system is linear. And for a system to be linear, it needs to respect two conditions. The first one is the homogeneity of the input and output relationship. So let's assume this. In this first block here, we have a system. When we apply x1 to it, the input x1, we get output y1. If now to the same system, we apply a scaled version of the same input, so a constant times x1, and if the system is linear, then the output is alpha y1. Alpha, sorry, not x. Right, so x1 gives y1. A scaled version of x1 gives a scaled version of y1 by the same proportion. Okay. For example, here, if we put an input like that through a linear time invariant system, and you get an output that is a sinusoidal waveform, once we reduce the input by half of its magnitude, then the output should also reduce by half of its magnitude. This is called the principle of homogeneity in linear systems. The second property is the superposition. If you now have a system whose input is x1, gives a output y1, and a input x2 gives a output y2, once we apply ax1 plus x2, the system is linear, then the output must be the linear combination of both outputs, y1 plus y2. x1 gives y1, x2 gives y2, x1 plus x2 must give y1 plus y2. Okay. Here's the same example. Let's say we have an input that is like that. We give that to our system, and the output turns out to be this ramp going up. If we give instead the system a sinusoidal waveform, we get another sinusoidal waveform in the output. What happens if we now take input A plus input B and we give that to the system instead? What should be the output? Well, the output is the combination of the output generated by signal A plus the output generated by signal B. So it should be a ramp that goes up with a sinusoidal wave modulated to it. So it should be something like this, where you see the effect of the ramp and you see the effect of the sinusoidal waveform. What happens if we scale A and B? Let's say we multiply A by 2. Well, then the ramp will go up faster. What happens if we change the frequency of B? Well, then the frequency here will also change. Right? So this is the principle of superposition. Another important assumption that you're going to make here is that the system is time invariant. This means that the properties of the system do not change over time. If I give an input to the system at time t, and I get a response y of t, and I give that same input to the system at a time t plus delta in the future, the output will be the same, y of t, but delayed in time. The output is the same, but is delayed in time because the input was delayed. And this is to say that the system is time invariant. That is to say that a mass, friction, electrical properties, all that do not change over time, which is hardly true in biomedical systems. What we can do is to assume that for a short period of time, this is true. And then we operate only during that short period of time. Okay, here is one example. Let's assume, for example, that this is a bell, and you will strike the bell at time 0. If we strike the bell at time 0, we produce this sound that decays over time like that. If we strike the bell at time 1 second, for example, then after 1 second, of course, when we wait 1 second to give the input, the bell will produce a sound in the same way. If you now strike the bell at 0 and then I want in 1 second, then the output will be the combination of both sounds. Right? And this is because the system is linear and time invariant. Right? And this is, again, a simplification that we need to make in order to be able to model mathematically some systems to be controlled.
Professor?
Yeah.
Can you explain why this system is time invariant?
Why the system is time invariant? Because in the case of a bell, for example, none of the properties of the system changed over time. The mass remained the same. Friction between the bob and the bell didn't change. Mass is the same. Atmospheric pressure is the same. Gravity is the same from time 0 to time 1.
Oh, okay.
Dynamic properties of that system remain the same, which is not the case in physiological systems. Things may change from time to time, but the assumption we need to make is that during the time we are operating, the system is time invariant. And we don't have the tools in this course in linear control systems to deal with systems that change over time that are time invariant. There are tools out there, but that's a different topic.
Cool, thanks.
Okay. Another example is causality and memory. I think there's some typos in the version you have there. If that's the case, please Check that. A causal system is a system whose output depends only on the current input and past input. Here's one example. If you have a capacitor and you want to calculate the voltage across that capacitor, we know that that depends on the integral of the current over time times 1 over C. Let's say this says that the integral is looking at the past current that is flowing through the capacitor, and you take the integral over time, which means that we are looking at the past behavior. So the system is a causal system. It depends on the past behavior. It also depends on the current through the capacitor, and therefore the system is said to be a causal system. It does not depend on future current. In this case, it wouldn't make sense. The only way we would have a non-causal system would be where the current input would depend on the future desired outputs, right? But that doesn't exist in nature. We need to create that artificially using a control system. So the system, any dynamic system, will be a causal system. In this case here, we can clearly see that through the integral, because the integral, again, is the integral from 0 or from negative infinity time to the current time. So you're looking at the past behavior, taking all the integration and including the current behavior to determine the voltage. So that's what we call a causal system. The next element we need to determine is whether the system has memory or not. The system is said to have to be memoryless when its behavior only depends on the present input. For example, a resistor. The voltage across the resistor only depends on the current flowing that resistor at the time of observation. It does not depend on past input. So the resistor is said to be a memoryless element. Another example is a damper. If you look at a force in a damper, the force developed in that damper only depends on the current speed of the damper, not on past, not on future speed. So the system is also said to be memoryless. So is an ideal damper causal? Yes. Is an ideal damper memoryless? Yes. What about an ideal spring? Would you say that the ideal spring is a causal system? I would say so, because it only depends on either past and current, or current values of the input. Is an ideal spring memoryless? Is an ideal spring memoryless? Any guesses?
No.
Why not?
Because it has a memory of what happened to it. Like if you pull the spring and it's like, vibrating.
Right. I see. Okay, so if you pull a spring and you look at the force deployed in the spring at this time, it only depends on how much the spring is stretched at this time. Right? It's not dependent on how it got there. If you look at an instance time t, right? But that's a very good confusion to have, because that clarifies the concept. If you stretch a spring, the process of stretching the spring is irrelevant of how much the spring, how much force or energy is stored in the spring at time t, which is not the case in the capacitor. See, the capacitor, if you want to look at the voltage, you need to look at past current, because you're integrating all the currents, right? Because you're accumulating the current in the capacitor, right? So in fact, the ideal spring E is indeed memoryless. Okay, but that's fine. Are dynamic systems causal systems? Yes, most dynamics, or all dynamic systems, will be described by differential equations, and therefore they are indeed causal systems. We need to observe past behavior to predict future behavior. Are there any questions?
Sorry, so the answer to the is an ideal spring causal is no?
Yes,
just wanted to make sure.
Yeah, so it is causal because it only depends on current inputs, not on future inputs. And is an ideal spring memoryless? Yes, it only depends on the current state of the spring. So the answer is yes and
Thank
yes.
you.
So what about after the spring has been released and there it might like be like vibrating essentially? Like would that make
Yes.
it memoryless still?
It would still, because we cannot look at vibration over time. We need to determine one snapshot of that. Just one instant in time. If you look at one instant in time, at that instant, it doesn't depend on how the spring got there. It just depends on how much, if it is stretched or compressed, and by how much.
So by definition, that's like a property of causal systems or okay.
Not all causal systems are memoryless. Mostly static systems are memoryless, but causal systems are not necessarily memoryless. The capacitor is an example of a causal system that has a memory because it depends on past inputs.
Professor, can you give an example of the dynamic system?
A dynamic system would be a mass spring system, for example. If you attach, let's say, if you attach a mass like that, if they have a mass here, a spring, like that, and you apply a force to it. This system is a dynamic system. We have, if you write the equations of motion for this, we'll see that in detail later, but I'll just give you the example here. If you write the expression, the equation of motion, we should have something like this. Sum of all forces equals to acceleration. That will give us this expression. So if you now want to solve this differential equation, you need to integrate this twice because of the second derivative here of position, which is acceleration. So integrating this twice means that we created memory in the system. Here is one integral, here's another integral. These integrals are looking at past behavior of the system to predict current behavior. And therefore, the mass spring system is a dynamic system, is a causal system, is not memoryless. We have two integrals here. Okay, don't worry about this equation for now. Next lecture, we're going to go through them in detail. So you have 10 minutes left. I'm going to go to exercise 1. We're just going to erase what I made here. And let's do one exercise here before we go today. So here we have a myoelectric controlled prosthesis. Prosthesis is controlled via electrical signals generated naturally by muscles. We sketch a control diagram for the prosthesis, specify the desired output signal, sensor, the actuator, the controller, the reference signal, and the error signal. So I'll let you, as I erase what I just did here, I'll let you guys think about this system. So that's the system we discussed earlier. Let's create a control diagram to, let's say, control the position of this prosthetic hand and identify all the elements needed to implement this. So there is no single solution to this, what you're going to do now, because it depends on how detailed we want the system to be. Anyway, let's assume that we are controlling the position. So the way we want to do this is that we want to measure muscle activity using a sensor and convert that muscle activity into mechanical motion for the prosthesis, and then make the hand go from point A to point B. How can we do that? So let's try to do that. So what is the first element in the system that we would need to make it happen?
Sensors.
Sensors, very good. We need sensors to know the position. Yeah, to know the position. So we need sensors and you need the actual position. So let's start maybe by defining the desired position. Let's call this desired position. And as suggested, let's also have a actual position, the current position. So this is where the hand currently is, and this is where we want the hand to go. We can now create an error signal, and this error signal is simply the difference between the two. If I want the hand to move 10 millimeters, then the error is 10 millimeters. Okay, what do we do with this error? What is the controller in the case when you want to move your hand? Which element in your body takes the decision of how much to move the hand or how much muscle activity to input in your arm?
Your brain.
Your brain. Very good. So this signal goes to the brain, and the brain decides how much muscle activation is needed to move your hand from point A to point B. And it's very intuitive. If you want to move your hand by 10 millimeters, your muscle activation will be something. If you want to move it by 1 meter, you'll see that your brain will send a stronger signal that is proportional to the error. All right, so the brain then sends signal to the muscles. So here we have the muscle. What happens now? If we want to control a limb that is not there, we need to somehow detect this muscle activity. So we need the EMG, the myoelectric interface. Right, that is now somehow measuring the muscle activity and converting that into an action that will move the arm. So now we can put here just one block for the prosthetic arm. So this includes all the actuation system, everything. Right? We have a signal that we capture. We now convert that signal into motion. And this is now the hand moving. So here is motion. Motion happens. And then we measure this motion with a sensor. And this sensor now gives us the actual position. So this is the actual position. This is motion, this is position, and that goes back into our control loop. Okay, so this closes the loop. Now, of course, this is a somehow simplified version of this control scheme. We could have expanded this, for example, to include a actuator, a motor, a servo motor, or something. We could have included a dynamic model for the dynamics of the arm itself, mass, friction, inertia, all that. We could have expanded this block more if we want. Okay, but this is the basic structure. And you see, again, the key thing in control systems is that this works in a closed loop based on an arrow of how far we are from where we want it to be. And if you think about it, it makes perfect sense. When you want to move your arm from A to B, we don't take actions based on the desired location only. We take actions based on how far we are from the desired location, and how far we are from the desired location is the error signal that we see right there. Okay, so in the example, we need to define the desired output signal. So here it is. This is the desired output signal. That's one. What else? We need the sensor. There it is. Sensor. That's number two. What else does the problem ask for? The actuator. The actuator is inside the arm there. I didn't specify it, but it's inside there. The controller. The controller in this case is the brain, because we're dealing with a human. If this was a separate system, then we would replace the brain with a digital controller, where the human here acts as the controller. The reference signal, which is another name for desired signal, right? Reference and desired is the same term. And the error signal, which is number 6 right there. Okay, so this closes our loop. And that's pretty much it. Any questions? Any questions?
Hi, I was just wondering what the EMG interface does.
The EMG interface detects muscle activity. It converts muscle activity into an electrical signal. Right? So if you want to control, let's say, this part of the arm, of course, the arm is not there, so you need to measure it as close as possible to the arm. And that is basically electrodes placed around the arm. And when your muscles are activated, it will convert that electrical activity into a electrical signal, which would be the output here. So this is muscle activity is the input, electrical signal would be the output.
Okay, thank you.
Yeah.
So the definition for the actuator would be whatever is being controlled from the electrical output.
So whatever creates, in this case, it would be whatever creates motion. It could be a motor, a servo motor, something like that.
Like the muscle wouldn't be considered an actuator because it's being directly controlled from the controller.
If yes, if you had an artificial muscle here to do the job, yes, that would be the muscle. If we wanted to do this not with just with a natural limb, then yes, then the muscles would be the actuator. Very good.
So,
yeah.
Why is the desired position the reference signal?
These are just terms, the terms that we use in control engineering. The desired and the reference is where we want it to go. Right, so that's the desired behavior of the system. That's what we would call them. It's just a different term for the same signal.
Okay, thank you.
Yeah. Anything else? Can you guys see the writing properly, or is it too dimmed?
No, it's clear.
It's fine.
It's
Okay, good. All right. Anything else? Any other questions? So next, in the next lecture, we are going to be interested in.
Sorry, I have a quick question.
Go ahead.
Shouldn't the reference signal be like the actual position of the arm? So you use like that knowledge to like develop something to get to the desired position. So the reference is like where you're coming from, and the desired is like where you want to go.
So the way you're coming from is here, right? It's the actual position.
Yeah, isn't that meant to be the reference?
No, the reference is the reference of the behavior we want, not the reference of the current state.
Oh, that makes sense. Thank you.
Professor, what's the difference between the desired output signal and the reference signal?
There's no difference. It's the same. It's just two terms that are used all the time in control systems. That they mean the same thing.
Okay, thank you.
I just wanted to introduce you to both of them because in the textbook they typically change from one to another. Anything else, folks? Here? No? Okay. So if there are no further questions, do we have time for another one? Or if we rush through exercise 2, perhaps. Well, we don't need to finish it, but I'll let you think about exercise 2. Just take a look at it. We still have 4 precious minutes. So take a look at it. In this case, we want to develop a system to control anesthesia level of the patient using some sort of drug administration. And we want the surgeon or the anesthesiologist to be part of this control system. So I'll let you think about the main parts of this system and how we would integrate them to form a closed loop control system to control the level of anesthesia. As I erase here, and then if maybe we have time to do it. And then later I will add these notes to the PDFs and then post them. But something I noticed with the first lecture here is that I'm getting a lot more questions than usual, and that's great. That's pretty good. So let's keep it that way. All right, folks. So let's do it. And we have 2 minutes. We'll just put the main ones here, the main points. So how would you guys implement this thing? What would be the first element?
Sorry, Professor.
Yeah.
There's also a question in the chat about what does EMG stand for again?
Is myoelectric signals.
EMG? Myoelectric
EMG.
signals?
Yeah.
Oh, okay. Cool.
For the
Okay.
desire, sorry, I was gonna respond to your question.
Yeah.
Would it be the desired drug amount?
Very good. So the first one would be the desired drug amount. I will put a percentage here. What else? We need to define the current as well. We create an error. Right? Now we need to take this error and somehow create a logic. Let's call this a controller. And the controller will tell us what actions to take. How do we inject the anesthesia into the patient? Maybe with a syringe pump. So I'm gonna write here just pump. This pump now injects something in the patient, a level of anesthesia, amount of anesthesia in the patient. So let's have the patient here. That's the poor patient. And then we measure somehow the level of sedation. So this is the sensor. The sensor gives us the effect, and the effect is measured back into the current one. Where would the anesthesiologist be? We could put the anesthesiologist here. Anesthesiologist. And the anesthesiologist would define, for example, the desired drug level based on how the patient is responding, based on how the patient is looking, and would also maybe set some parameters in the controller. And if you want to also go one step ahead and say that the anesthesiologist also surveys the pump, you can also add something else there. Okay, and this closes the loop. Of course, there are different interpretations of this control system. We could develop it more or less. The role of the anesthesiologist here is also up to discussion. Okay, so it is time to wrap it up. So in the next lecture, we are going to be interested now in this first part of our problem here is to model how the system responds to certain commands before we close loop, before we develop a controller even. Right? So how exactly these two elements can be modeled? What is the relation between the input and the output in the system? So we're going to start our study with mechanical systems modeling, and we are going to then move on to describe them in the form of differential equations. We are going to move on to electrical systems and then electromechanical systems, and we're going to build it up from there. Once you're comfortable with this behavior, with these models, then you're going to start developing sophisticated controllers to make these systems move now from state A to state B. Okay, any questions?
Sir?
Yeah.
I just wanted to say that this board that you're using it's really nice, at least in my opinion. It's like really clear to see. Just wanted to know.
Cool.
Yeah, it's really, really nice.
Nice, good to hear, because it wasn't easy to put it together. Good.
Thank you so much.
Well, thank you, everybody. If there are no further questions, I will see you again on Tuesday. So I won't have office hours today. I will start next Tuesday, right after the lecture. If you have any questions coming from and you want to clarify them before them, just send me an email. All right. Thank you, everybody. Have a good day.
Thank you.
Thank you, Professor.
Thank you.
Thank you, Professor.
Thank you.
Thank you.
Thank you.